In this screencast, I'll show you how to start the Simulink simulation environment and set the working directory. So once you've started MATLAB, you can set the directory where all the files will be saved for your Simulink simulations by using this bar here, and if you click you can select a folder, and that's where your simulation files will be saved, and any other associated files that get generated, they'll be saved in that location too. So it's important to set that correctly at the beginning, especially when you're coming back to open things, so that MATLAB and Simulink can find all the files that it needs to run your simulations. Now, to start the Simulink simulation environment, click on the button up here, and this will bring up a window with different options that you can click on. For the sake of this window, for this video, we're just going to click on blank model. That will then bring up a simulation environment that we can use to build our simulation, and we do that by putting together different functions and connecting those up and programming those. So to bring up a list of different functions that we can use, we click on this button here, and this will bring up the Simulink library browser, and we have these different functions, all sorts of different options that we can use, and these are built up of blocks of code in MATLAB, but the Simulink environment just means that we can build these together much more easily than having to write line by line code to create our simulation. Overall, that is how we can set the working directory for Simulink and start the Simulink environment. In this screencast, I'll show you how to create a simple simulation using Simulink. Now, any simulation needs a source and a sink, and for this simulation we're just going to simply use a source connected to a sink, and to find these we click on the library browser and bring up the different blocks, and for the source we're going to use a sine wave generator, so we simply click on this, hold the button down and then release, and that is then put into place. For the amplitude we'll just select 1, and then we need to bring up the library again, click on sinks, and we're going to use a scope to see what is happening in the simulation. Again, click, drag it over and then release. The number of ports is just 1 for this example, and then to link these up we click on this arrow, drag across and then release, and these two are now linked together. If we double click on the sine wave, there are different options that we can set. We're just going to leave this with an amplitude of 1 and a frequency of 1 radian per second. Click OK there, and we're now actually ready to run the simulation. So we click on this round button here, this play button, and that has run the simulation now. We double click on the scope, it will bring up this graph, and we can see the sine wave that's been generated by this sine wave function. We can click to zoom in, we can click to rescale everything back to the original settings, but overall that is how we can create a very simple simulation in Simulink. In this screencast I'll show you how to use a simple mathematical operation within your Simulink simulation. So here we have a basic setup with 2 sources and 1 sink. We have a sine wave which has an amplitude of 1 and a frequency of 1. And we also have a ramp that has a slope of 0.3. And if we go to the library and click on math operations, and then click on the add function and drag and drop that onto our simulation, we're going to have ++ here to show that we're adding 2 signals together, and then we can link this up by clicking on the output arrows from the ramp and clicking on the input arrow to the add. Do the same for the sine wave generator, and then we'll link up the output from the add function to the scope. If we press the run button, the simulation will compile and run, and then if we click on the scope it shows the overall output from those 2 signals being added together with it in the simulation. Overall, that is how you can use a simple mathematical operation within your Simulink simulation. In this screencast, I'll show you how to differentiate and integrate a signal within your Simulink simulation. So here we have a basic setup of a sine wave generator, amplitude 1, frequency 1, and that's linked up to a scope. And if we run this, we'll see a nice sine wave, but the purpose of this screencast is to show you how to add in extra functionality where you can differentiate a signal and integrate a signal. So if we click on the library and click on the continuous option, then we can put this derivative block on, and we don't have to fill that in, we can just click escape, and we can link this up to the sine wave generator. To do this, we have to click on the input arrow and then drag that up to the line there, and that is now providing us with a connection into this. To add an extra port to the scope, we right click and then go to signals and ports. Number of input ports, we'll set that to 2, and then we can link this up so that we'll see what's happening, and we'll run the simulation, click on the scope, and now we can see the yellow line is the sine wave that's been generated, and the blue one is the derivative of that that's been worked out for us using this derivative function. We can also add an integrating function. So again, if we go to the continuous functions and click on this block here, we can drag and drop that, and the initial condition is just we've got 0 area to start with, and again we can link this up by clicking on the input here and linking that up to a signal from the sine wave, and again right click, signals and ports, we'll change the number of inputs to 3 this time, and then we can link this up here, and we can run this, look at the scope, and again we've got the yellow line which is the sine wave, the blue line which is the derivative, and now we've got this orangey red line that is the integral of the yellow line. So overall, that is how you can integrate and differentiate signals within your Simulink simulation. In this screencast, I'll show you how to introduce lags and delays in your Simulink simulation. So here we have a basic setup with a step change. So what's going to happen after 2 seconds, there's going to be a change from an initial value of 0 to a final value of 1, and we're going to see the output on the scope. So if we run this, we can see that this is what happens, that to start with we're at 0, and then once we get to 2 we jump up to 1 on the y-axis, and that just continues until the end of the simulation. Now if we want to introduce a delay, we can go to the library, click on continuous, and then click on transport delay, and then drag and drop that in to our simulation, and we'll put a delay time of, let's say, 5 seconds. In fact, if we double click on there, we can just make sure that this is all set up how we want it to be set up. So the initial value is going to be 0, and then that's going to, after 5 seconds, change to whatever the new input is in here. So to connect this up, we need to click on the input, drag and drop, and then unclick once we're on there. The scope, we can right click, change the number of inputs to 2, and we can link this up here, and then we can run the simulation, and it will show us that it took 2 seconds until the step was triggered from the source, and then this blue line represents what's happening with the delayed signal, and we can see it took an extra 5 seconds for that to change its value. We can also introduce a lag where there's a gradual change from the initial value to the final value. Again, within the library and in the continuous options, we can click on transfer function, drag and drop that into our simulation. We'll link this one up to the step change. We'll change the number of inputs to 3 on the scope, and we'll link that up. Within this there are options for the numerator and the denominator, and these values can be changed and tweaked to give us different transfer functions and therefore different performance in and different sort of characteristics of the lag. For now we'll just leave this with the default settings, click OK. We can run this, click on the scope, and we can see that we've got this extra line here, this orangey red line, where there's a gradual change from the initial value of 0 through to the final value of 1. Overall, that is how you can introduce lags and delays into your Simulink simulation. In this screencast, I'll show you how to create a subsystem in your Simulink simulation. This can be useful because you can gather different functions together to create a new function, and it just helps to make the simulation a bit simpler. So the first thing that we need to do is finish off this simulation here. This is for a PID controller, and we need to add a sink and a source. So the sink will be an output that we'll put onto here, and that will be port number 1. We'll just move that over to where it needs to be, connect it up, and we'll also add a source, which will be this input block here, port number 1, link that up, and then we simply click, highlight everything, and then release the mouse button, and then we right click, and then we select create subsystem, and there we have our subsystem created, and then we can go on to use that for other things. We can build that into a bigger simulation, like a PID control loop, for example. And overall, that is how you can create a subsystem in Simulink. In this screencast, I'll show you how to change the model configuration parameters in your Simulink simulation. So what we need to do is click on this cog icon here, and this will bring up this window where we can change various parameters. So for example, we could extend the time of the simulation, we could change this to 100, we can select different solvers for the simulation, and we can also select where we have variable step lengths or fixed step length for this, and there's also additional parameters that we can set in here. If we just set it so that the only change we make for now is to make this 100, click OK, and we'll run this. And if we look at this for this simulation where we've got a sine wave and a scope, we can see that our sine wave has come out like a sawtooth, really, rather a bit of a mess really. It's oscillating and it's all jaggedy. And the reason for this is that we've got a variable step length, and it's not giving us the granularity and the resolution that we'd need to be able to see this in the detail that we want to. So if we close this and go back to settings, and if we switch to a fixed step length, and then if we put that to 0.1 and click OK, and rerun the simulation, and then we can see that this is much closer to what we'd expect. In fact, it looks much better in terms of the sort of shape and the regularity of these waves. And we can also zoom in a bit, hopefully, and just see that that is much closer to what we'd want for this sort of pattern. And overall, that is how you can start to make some changes to the model configuration parameters in your Simulink simulation.
Hello everyone, and welcome to the Quadcopter Modeling and Control webinar. I'm Ryan Gordon, here with Michael Carone.
Hi Ryan.
Hi, Michael, and we'll be covering the content today for the quadcopter model and control. And throughout the webinar today, unlike a lot of our webinars, we'll actually be able to answer some questions during the event. So if you have any questions as we go through all of the content today, please feel free to type it in the Q&A area of the WebEx, and Michael's going to help me help relay those questions to me when appropriate, and we'll be covering a lot of those questions today. And to get started, I'm just going to bring up our finished quadcopter model. And I've already run the simulation here, so this is just the animation of that simulation. And essentially what the model we're going to build today, and this is just going to be a big overview of the model, is I'm going to show you how we built this quadcopter that will start on the ground, start up, and enter into a hover mode and a stable hover flight. And as you can see, over time, it's just going to stabilize at, should be about 1 meter in altitude. And yeah, this is what we're going to do today.
Sounds good.
All right, so coming back to the PowerPoint, why quadcopter modeling and control? First of all, quadcopters are really popular. If you're watching this webinar today, there's a good chance you might actually already own a quadcopter. And it's a great way for us to showcase how model-based design works. In addition to that, the concept that we're going to show today of modeling, simulation, and control can be applied to a variety of systems, not just a quadcopter. So if I show you how to build up a model of a quadcopter today, you could go use those techniques and build up a model of an airplane, of an automobile. All sorts of things can be applied. And of course, finally, quadcopters are fun to fly. Okay, so there's three main things we're going to cover today. And normally we go into great detail about a lot of, try to get to the beginning and end of the whole design process. But quadcopters are very complex, at least the way we're trying to model ours and get a high fidelity model. So we're only going to cover these three main points today. So don't worry about trying to follow along exactly, as this webinar will be available as a recorded version on the website in about a week's time. But try to follow along and look at kind of this big picture way we're modeling this quadcopter. And think about, if you have a CAD model of your system, we're showing you how you can import that directly into Simulink using the SimMechanics link. And finally, we're going to show you we're only going to tune one loop of the quadcopter today. But we tuned all our loops using the same methodology, so you could apply this to your entire MIMO control system if you can decouple the loops.
Right, so the intent here is to really show more of a workflow than to show a tutorial of this is how you use SimMechanics, this is how you would do control system design with Simulink. This is really just to give you a broad brush overview. Here's kind of a flow between modeling, simulation, and making sure everything works right.
Right, and I'll try to make the model available. I'll put up my email at the end of the webinar. And if you're interested in getting this model that we build today, you can send me an email and we can get that model to you. Some things we'll be covering later, hopefully in another webinar, is improving the model fidelity, real-time simulation and testing. What I'm sure a lot of you out there are interested in, if you're doing quadcopters already, is deploying to targets. If you're doing ArduPilot Mega already, you can go to the MathWorks file exchange, and there's already block set that's been developed to help simplify that process. And we've got some stuff in the works for Pixhawk PX4 as well. And then finally doing some flight testing and matching our model to our real hardware. That's something that we're coming really close to doing here, and something we think is really exciting that we'll be able to show in the future. So to get started with SimMechanics, if you're not familiar with SimMechanics, it's our multi-body simulation environment for 3D mechanical systems. And the reason we use it today is it's going to simplify the buildup of our dynamic system, and it's going to integrate with other physical modeling libraries. So when we build up the electric motors and the thrust for the props, it's going to simplify our ability to do all of those different things without having to derive the equations. And so I'll come into Simulink, and I've got this little demo I like to show how SimMechanics works.
Right, so this is a Simulink model that contains SimMechanics blocks. Is that what we're looking at right now?
Right. And so if you're familiar with Simulink, down here we've got our Simulink blocks. There's actually only a couple in this model. And up here we've got all of our sim mechanics blocks. And there's 3 components, and I think I'll first play the simulation and open up the Sim Mechanics Explorer to show you what this model looks like. And if I bring this over to the right-hand side, we can kind of look at what's going on in the Explorer and show how that's represented here in the diagram. So first I've got this arm, that's this big gray arm here, that's connected, and we use these rigid transforms to tell sim mechanics where all the different pieces of our multi-body system are. And that's connected using this rigid transform to this prop, and it's parallel on each side, so underneath the Explorer here it's the same thing, except going in the opposite direction. And we use this revolute joint to define the motion around the z-axis here so that this prop can spin. And in addition to that, we've connected this arm to the world using a revolute joint so that the arm can rotate around the world. And this is pretty similar to how a quad rotor works, except instead of having 2 props, you have 4 to balance the system. And so when I run the simulation, what I've done is I've added this step torque input into one of my revolute joints, and I've temporarily commented out that same step input into my opposite prop. So one of the props will spin, and let me run this. And what sim mechanics does is it automatically derives the equations of motion so that the torque generated from the spinning prop will spin the arm of the system.
Okay. So the way I'm looking at this model is that you've got multiple bodies defined. You've got an arm. You've actually got 2 props. The other one's hidden.
Let me kind of move that around. Yep.
Right. So you have 3 bodies, and then between those bodies, you're defining how they're connected to one another. Basically the constraints that are placed on the connections between these 2 bodies, or 3 bodies.
3 bodies. Yep.
Right.
So by defining these revolute joints, I'm able to tell sim mechanics how I want these bodies to move relative to each other.
Okay, and then you're injecting a stimulus in order to rotate the prop, and that's how it's moving around.
Right.
Okay.
And so now if I uncomment this gain, I'm essentially going to make the prop spin in opposite directions. And when I run this simulation, what we'll see is that because sim mechanics derived these equations precisely for me, it's now a balanced system, and the arm is no longer moving.
Now, one thing that's different with this compared to Simulink models that maybe folks watching this are familiar with is the connections between these sim mechanics blocks aren't one-way directional flow.
Yeah.
You see basically squares at the ports. So can you explain that just a
Sure. So when I hit that play button, sim mechanics under the hood is essentially assembling this multi-body system for me and deriving all these equations of motion for the entire system. And when you have a multi-body system, it's much like a feedback loop you would have if you built it up with Simulink blocks. You would have what we call an algebraic loop. I won't go into detail about that if you're not familiar, but essentially the motion of the arm is dependent on the motion of the prop, and if the prop gives another force, or if the arm gives a force on the prop's motion is also dependent on the torque that the arm's moving, and it kind of creates this feedback loop of motion with the multi-body system. Now in Simulink, the way you would resolve that is by putting a delay in the feedback loop. But sim mechanics takes care of that automatically, and that's why it uses these square connections, because everything is interconnected as a system instead of with Simulink. And if you're not too familiar with Simulink, I hope you'll bear with us, but with Simulink, we use these arrows because things kind of flow through the arrows in one direction, and these connections are bidirectional.
Okay, that makes sense.
All right, so this is just kind of our brief overview of how sim mechanics works and why we like to use it. So I see here that I've got a balanced system. I can add 2 more props on this manually, but as I build this up, I want a system that actually reflects my quadcopter exactly. So this is kind of the heart of what I want to show today, because I think this really allows you as an engineer to get started very quickly with your model and simulation of your system. And what I'm going to do is I'm going to import a model from SolidWorks of the quadcopter and build a dynamic simulation on top of that. And if you've ever had to build a simulation using the equations of motion, you know how complex it can be to write all this out and debug it and make sure you've got all the masses and moments of inertia correctly defined. And what happens when I use SolidWorks, assuming that my model, of course, is well defined, is that all of this is taken care of for me during the import process. Normally I would open up SimMechanics here to show you how this import works, but I'm on this webinar computer that we use, and we don't have SimMechanics on here, so I just made a short video to demonstrate this process. And so what I've done is here I've got SimMechanics link installed on my PC, and here you can see the SimMechanics link dialog that comes with SolidWorks after you install SimMechanics link on your computer. And I've got my quadcopter model already designed for me. We actually received this from our supplier, so there's some interesting things I'll show you about how to work through some issues you may come across when you do this import if the person who designed your model didn't keep you in mind when they designed it and all the joints aren't properly defined. But I'll continue on, and as you see, I'll come into this export menu, and it will say SimMechanics second generation. Second generation, I think, has been out since R2012B, R2012A timeframe. And I'm just saving this as an XML file. When you do this export, it's going to save it as an XML file. And I actually fast forward this a little bit. It takes about 5 minutes to do. And what it will do is start going through all these different components and translating them into XML that SimMechanics can start to read. And as you can see, it's just processing on my computer. SolidWorks turned white as it was processing. I'm just trying to show you the kind of the real world use case of how this works. And at the end, it says the SimMechanics import XML file has been saved to file quadrotor v2, which is the file I saved it as. So that's the basic process of how you would export it out of SolidWorks. And once you've got it out of SolidWorks, I'll add this to my path because this is where my model is. You use the function SimMechanics SM import, and I'll use the quadrotor file that I've made previously. And if I come into my SolidWorks model area, you'll see I've got a number of different files, but I'm using this quadrotor XML file, which is similar to the export I just performed. It was just done in an older version of SolidWorks, so I know where all my components line up when I go through it to make it a little fast for you folks on the other end viewing the webinar. And you saw it just imported that entire XML file fairly quickly. Mm-hmm. And when I maximize this, these lines and blocks should be fairly familiar to you. And what I'll do is I'll hit the play button. And I can see that my quadcopter here in the SimMechanics Explorer, oh, it looks like it started to move. So first thing I know is that it's going to add gravity to my system. And so if I have gravity and nothing to prevent my system from moving, I need to negate the gravity so I can start to work with my model, make sure all my components are connected correctly, and then I can come back in and add the gravity back.
One of the advantages of simulation, you could just eliminate gravity. That's
not a problem.
Right, not a problem.
Okay, so let me come back in here. And I can see now when I hit the play button, nothing's really moving. But there's a couple inconsistencies I noticed with my system. I'd like to see my props start to move. I'd like to see Z be positive down. If you're in aerospace, you may be familiar that Z is usually positive downwards. And here I see the Z is positive upwards.
Right.
And I guess the first thing I'll do is I'll get one of those props to move. So I'll come in here, assembly rotor end, which is where those props are, and I see here's my rotor. And I'll just disconnect this line. And again, this is just something I'm doing because my the person who developed my model wasn't really paying attention to what I needed from the CAD model. He was putting it together for his own purposes. And so now there's a couple inconsistencies that were generated from the import. And so it's just loading some of my libraries for Simscape.
And this actually is a nice way to answer the question that came
Sure.
in. Does sim mechanics come as part of MATLAB, the MATLAB package like Simulink? So Simulink is separate product to MATLAB. Of course, Simulink sits on top of MATLAB since MATLAB is the platform, and then think of Simulink as the platform for sim mechanics. So it's kind of an analogous situation where MATLAB is the platform for Simulink.
And so now I've got my Revolute joint connected to my rotor, so I would expect my rotor to spin. And to make sure this works, I'll simply actuate my rotor using a torque. And somewhat arbitrarily, I'll just add a default value of 1. And so using the physical signals instead of Simulink signals, because this will allow me to build up my entire system in Simscape blocks, I'll just connect a default constant value of 1 and hit the play button. And when I come to my Explorer, I notice right away, I've actually got to slow it down, it's going to happen so fast, that my rotor just goes crazy.
Okay, so you added an input force to the rotor, and it just disconnected and flew away.
Exactly. And so this is, again, one of those things you might notice if you start going through your model and you're trying to figure out what's wrong. And so I know from experience that up here on the top level, all these 6-DOF joints really don't make a whole lot of sense. And the reason my rotor assembly was able to disconnect is because I had this 6-DOF joint here. And I can simply delete that joint. Oh, it looks like it's actually still running. And I can delete that joint.
Probably need to get rid of the X.
Yep, there it is. Thanks, Michael.
Yep.
And now if I do that, if I just get rid of that 1, I'll see that it will start to spin, but it's still not performing as I would expect it to. Looks like it's...
At least it didn't fly away.
Yeah, it didn't fly away, but it's not doing what I would hope it would. So, okay, so it's spinning a little bit. It looks a little choppy. And that's just a matter of the solver not working as fast as I would like. But it looks like it's going okay. And now I can get rid of the rest of these 6-DOF joints because I know these are not in the right place either because they're all attached to the different rotor assemblies. And connect these up. And now if I run that simulation, what I would expect it to do when I turn this rotor, if you remember from my previous demo, is to spin this entire system. And it's not doing that because between the world and the quadcopter, I don't have a 6-DOF joint. So what I'll do is I'll come back into my joints, grab a 6-DOF joint, and connect my quadcopter to the world using a 6 degree of freedom joint. And you can see these little B and F on every block, and that just stands for base and follower. So the world is my base, my follower is my quadcopter. So now if I run the simulation and I come back to my Explorer, we see now I've got the whole thing spinning. That looks like it's doing what it's supposed to be doing. Yeah.
Now, this animation, is this something that you develop separately, or are you getting this for free, essentially, because you're using sim mechanics?
This visualization all comes with sim mechanics. So as I built up my previous one, you saw it was very square and very simple animation. That's because I built it up using base sim mechanics blocks, and I didn't go into too much detail to define how they would look.
Right.
When I do the import, the visualization component is already done for me. So it's using these are all sim mechanics blocks, and then it adds a visualization on top of them based on how it was defined in the CAD model. Okay,
so you're basically combining the strength of SolidWorks and developing like some complicated geometries, importing that into sim mechanics so that you can then run simulations and actually watch these things move and see how they're connected to one another, and then you'll show later the controls aspect of that as well.
Precisely.
Yeah.
Precisely.
Okay.
And as I mentioned earlier, the one last thing I want to add is Z positive down. So any aerospace folks out there are probably familiar with that coordinate system. So what I'll do is I'll add this transform in, and I don't need a translation. And I'll do a standard axis rotation along the x-axis, And if I come back to my Explorer, this is going to help me actually understand how I want to rotate. So if I rotate around this x-axis 180 degrees, and it's actually already at pi radians, so I can actually do, should be pi over 2, should do it. Let's see. And I can say Z down positive in my view convention. And it looks like it was not what I expected. So I'll simply manually go to degrees here and make sure I get it right. And I can actually just do an update diagram, which I do by hitting Control D.
And remember, pi radians is 180 degrees.
Oh, that's right. Basic math.
That's right.
So if I come back to my Explorer, so after making that's little mistake there. That's why I've got Michael here to help me out.
Well, no, that's why you've got some mechanics to help you out and prove that was the case.
Yeah. But now you can see that Z is positive down. So I define my view convention as Z positive down here. Again, because it's very common in aerospace applications. And I can take a look at my system, and now I can run the simulation again to verify everything's working as I expect. And I see the rotor spinning, my quad spins. Everything's good in the world, and we're ready to move on and do our control system.
All right.
And one last thing I should add is that I would add the gravity back in here as well. And we'll show that in our bigger model. So now we're going to design our control system. I've got this bigger model I'll open up in a moment, but that does a little bit of the thrust and the ground contact, as I mentioned earlier. But what I have is this cascaded control system on the position rate and rate feedback. So I've got, in this particular model, I'm omitting yaw control for now. I don't define the aerodynamic yaw caused from the rotation of the props. I'm assuming things are symmetric. This is just to simplify my control design for now. As we move on in this quadcopter design and do future videos or webinars and show you guys how this all works, we'd have to add that in because obviously that is something that is required to control the quadcopter. But for simplicity today, I'm doing roll, pitch, and altitude control. And the way I'm going to tune these PID controllers today is something really new actually in Simulink, which is the PID control tuning using an estimated linear model. So don't worry about all those words there. I'm going to show you how that works. But before I get into this demo, I want to just give a brief overview of what the control system looks like. So you can see the three inner loop controllers here on the rates, PID on the roll, pitch rate, and the altitude rate. And then I've got PID controllers on the pitch, roll, and altitude. That goes into a mixer that's going to define how much PWM goes to each one of the four motors. And so that voltage command is going to drive the PWM. Okay, so let's hop back into Simulink, and we'll tune one of these controllers today. We'd use the same process on all of them. And you don't really need to know how to do control design to do this, but we really only have the time to do the one controller. And so here's our finished model. I actually use this for hardware in the loop testing. I put the controller on an Arduino. I connect that up to a Simulink real-time target box. I send my model over to the target box, and it runs in the loop with the hardware, and that lets me know that my controller is capable of running on the hardware at the right rates. All sorts of cool stuff like that. As I mentioned, we can't cover that all today. But I do want to focus on what I have over here for my plant model. So these blocks over here, these 4 blocks represent my plant model. I've got DC motors modeled using sim electronics. You know these are physical signals because you see these little arrows here are white arrows instead of black arrows, which are used in Simulink. I've got my external force. I use physical signal blocks. As someone mentioned, they want to define their own equation. I use those blocks to define the thrust for each prop. I've got my ground stop here. Again, that was another question someone asked, can you model hard stop with the ground? I do that in here. And essentially what I do is I model a stop on each of the 4 feet of the quad. And here, I'm using our content preview to show what's underneath this block. And these should be pretty familiar to you. These are my sim mechanics blocks. And I have the external force coming in to drive the prop. And I have a sensor for the rate of the prop and an external force here to add the thrust right at the center of the prop in sim mechanics. And so if you've never seen this feature before, I think this came out in, is this 13B, Michael?
Yes. Yes, it is.
And so you could come into here and do use the content preview feature to show what's underneath the block. So this is really great for us because normally I have to go in and out of these subsystems to show you how it all works. And so for us making webinars here at MathWorks, it makes it really easy for me to show you what's going on inside of here.
Yeah, it's also convenient if you don't. You show somebody a big model, they want to know just from a bird's eye level what is actually in that model. You can actually quickly tell if something is just a placeholder block as well. If it just has a simple input output, I'm going to develop that later. That's another useful way to use those types of blocks.
So up here, I've just got two subsystems. I can double click on one of these to change my settings between real-time and desktop simulation. I'm doing desktop simulation. I'm all set up for that. I have my roll and pitch loops in here, and I've isolated my altitude loop, which I'm going to show you in just a moment here. This subsystem has just some initialization commands. And essentially, the way the simulation works, and I've run this already, so I'll just show you what it's going to look like when it's done, is I have all these steps and all these signals coming in and out. But all it does is at 5 seconds, and you can see my little timer here in the lower right-hand corner, the quad turns on. I send a step response to send the quad on. I have this command 1 here that says go to 1 meter in altitude, and it just holds that altitude. Now, it looks like these props are moving slow, but as I mentioned before, there's this resolution of the animation because the props are spinning at about, I think, 1,000 RPM. They just look like they're running slow.
So it's like persistence of vision almost.
Yeah. If you ever seen someone take a video of a propeller spinning,
right?
It looks kind of funny because same type of
it's
visual.
the refresh rate in your eyes. Yeah, that's actually what it is.
So we get this quad that's hovering, and I want to show you how we made it hover. So I'll come into my desktop controller here and use my desktop controller. And here are those two PID controllers I showed you before. I got rid of the derivative part on my Z position because it was going too slow when I had the derivative damping it out. I've already tuned my Z velocity controller. And so what we'll do is this is kind of like finishing the control process. So I'll tune my Z position here. And what I'll first do is I'll take out a copy of this and comment it out. Mistakes happen all the time when I'm tuning my controller, so I'm just having one back up here in case things don't work out the way I planned.
Yes.
And one thing I do want to do actually before I get started is log my input here and record my signal so I can observe how things change over time. And so what I'll do is I'll put in the default values here. If you drag in a PID block from the Simulink library.
So this is included in Simulink.
This part is included in base Simulink.
Right.
I came here, I said I want a PI controller. The default values would be 1 and 1, and I set the sample time to 100 hertz. And so I can run the simulation as is. And I think I only maybe need 10 seconds here, so I'll modify this to be 10 seconds. And I can see that my simulation's running, and I can come to my Explorer and see its times kind of match up here. My simulation's a little slow. There's some techniques I could use to speed that up as well. And I can see, it didn't even get back down to where I needed it to be when I run it. So I'll run this at 2 times speed. Came up, and it's just very slow. And if I open up my data inspector, which will allow me to view my signals, I can look at my altitude versus my command. And, I think I can speed that up a little bit, and I'll use the PID tuners to speed that up.
So that data inspector opened because you logged the signal, right?
Right. I logged the signal and hit that red record button.
Right.
And so the way you want to speed up a signal with a control system is by tuning the controller. So I'll hit the tune button. This uses what we call Simulink control design, which is built on top of our controls products. And what it's going to try to do is linearize the plant. But I've got PWM signals in here. I've got all sorts of nonlinearities in my control system because I've already put my control system in here. So I get this error. I could resolve this error, but today I don't need to because I'm going to use this new feature to identify a new plant. So I came into this plant menu and clicked Identify a New Plant. And I see my plant identification window is now open. I don't have any input-output data yet. So what I'll do is simulate data. Now, if I already have data from my model, I can select any one of these to import that data. Since I don't, I'll simulate the data. I'll put in my commands to get this data that I need. This might be a little bit of trial and error. Control design is an iterative process, but I know the values I need to get this going. So I'll do a step of 0.5 amplitude. And if you look at this context menu here, you'll see it's going to measure the input to the PID controller, and it's going to open the loop at the input, at the output of the PID controller, which is the input command to the altitude rate controller. So I'm essentially saying, give me an altitude rate of 1 meter per second at 6 seconds, increase that by 0.5 meters per second, and record the data.
Okay, so can I just take a step back and try to explain what you're doing, and you correct me if I get anything wrong. So,
sure.
So you want to linearize this part of the model so that you can tune the controller attached to it. And so in order to do that, you are generating a linearized version of the model using system identification.
Yep.
And that's what you're doing right now. And then that's what you're going to use in place of the nonlinear model that you had before, and then you're going to be able to do your tuning that way.
Exactly.
Okay.
And so a couple of the big things that make this model tough to linearize is the PWM. That's that fast toggling. It's hard to linearize over that. We can do it.
Discontinuities.
There's some things we can do to make that work. And before this feature came out, I would have done those things to make it work.
Right.
But I don't need to do those anymore because now I can just identify a plant running simulations.
Okay.
And so what this does is it's going to run 2 simulations. It's going to run one default simulation without the step and another simulation with the step. So I have my initial response, my offset response, and then the difference between the two is the data that this will use. And so that looks good to me. Having run this before, I know it's gonna work well, and I can just click apply. You may need to experiment again and iterate on your process here to make sure this works for your particular system.
Mm-hmm.
So I close that. There's different structures. I'll start over here. So we always work left to right on these context menus. There's a bunch of different things I could do to pre-process my data. Fortunately, I don't need to actually do any of these today, but if you have data that's not as clean as my data is, there's all sorts of ways you can clean it up to make sure the identification will work well.
Right. So this would be if you were getting data from the real world, and that's
even in simulation, though, there can be discontinuities that occur, such as a delay, and a linear plant model can't handle a delay, so you have to remove that manually.
Right.
And then I need to define my plant structure. I'm confident this underdamped pair will work, and I can see how that's defined here as a second-order system. I also know from experience that I want to add a 0 because of this, the shape of my identification data, and I can click and drag things to make it fit better. But for this particular data set, I think it's just going to be easier to hit my auto estimate button and run the optimization routine. And you can see it's going to run through 20 steps of optimization. It's got a pretty good fit, 82% fit. And that's pretty close, but I'll just go ahead and hit it again. And you can see how fast this works on this estimation data. So it's not too bad for me to just run it a couple times to make sure the data is a really good fit. And now, I'll just show you, I've got 98% fit on my plant model. So this is what my plant model structure looks like. If I click Edit Parameters, these are the parameters that I optimized.
Mm-hmm.
And this looks really good to me. I think 92% is not too bad. So I'll save this plant. And I can get rid of the default plant that it chose. And I can see my initial response. And you may remember when I hit that play button, it did a big overshoot and then took some time to come down. And you can see it's going to take quite a while to come back down based on that linear model. So actually the plant that I have in there now, the controller, and I'll show the parameters over here while I tune, isn't too bad. It's just not as good as I think it could be. So what I'll do here is I'll start by going to maybe about 0.5 seconds and make it a little bit more robust. And I can see that the PID tuner is automatically adjusting my view as I go through the tuning process. And I can even go faster than this maybe on my linear plant model. So let me try 0.25.
So dragging those bars takes away the need of adjusting the PI parameters manually As
Right.
you see, it's automatically changing them for you. So you could concentrate on what you really care about, which is the response time and the transient behavior, not the values of the PI parameters.
Exactly, and it's also got those classical control requirements in here, such as gain and phase margin. So if you have requirements for gain and phase margin, you can make sure that you hit those requirements while using the same PID tuner and observing the step response. So here's something that's pretty fast. It looks like the step response looks pretty good. So I'll click Update Block, and I'll run my simulation. And I'll open up my data inspector, so once it's done running, should be pretty quick. So remember that first 5 seconds, it's just going to match here identically because it's just bouncing off the ground. And I could also observe this in my SimMechanics Explorer, but I don't want to pop those windows up and down too much.
Right.
And if I look at my altitude, I can see that's not quite what I saw in the PID tuner.
Yeah.
And one of the reasons for that is the linear model is only so capable of predicting my system performance compared to my nonlinear model. And so essentially what happened is I moved that PID tuner way too fast, and now I've got this very oscillatory behavior compared to...
That is not desirable.
Not desirable, exactly. So what I'll do is come back to my tuner, and this is one of my favorite things about using Simulink to do PID tuning. And I'll simply slow it down a little, and let's see, get a good overshoot there. Update the block, and run my simulation again. So now it's just going to take a moment to run the simulation again.
But this is the power of desktop simulation. Is you're not testing this always on the quadcopter in order to figure out the right values. If you're doing this on the real quadcopter, you could start damaging equipment quickly, which you're not obviously doing here.
And so now, I'm very quickly able to move those sliders, retune the controller.
That looks a lot better.
Run the simulation and know that my quadcopter is going to behave as I expect.
Right.
So now I can see, wow, this looks way better than my original.
Right.
Better than my poorly tuned. I did this tuning, but it didn't turn out the way I thought it would. And everything looks pretty good to me. And so what I can do now is come back to my tuner. I can simply close this. All the parameters have been applied. I don't really need to use my commented out block anymore, and I'm ready to deploy this to my target.
Okay.
So that's about all we had to show today.